Hi everyone, welcome to our Calculus for Civil Engineers series. I'm Engineer Hilda G. Hamsilani, and today we're starting with the very foundation of all engineering math, the real numbers and algebraic expressions, the language of algebra, what every aspiring engineer should know. But before we dive into limits and derivatives, we need to understand the language of numbers and symbols that make up every formula in engineering. Whether you're analyzing beam loads, computing material stress, or simply converting units, algebra is everywhere. So let's start building that foundation. Let's begin with the different types of numbers that we encounter in mathematics and engineering. Collectively, they are called real numbers, and they make up the foundation of almost every engineering computation. So, what are the types of numbers? The real numbers includes the following: the natural numbers. These are usually used for counting, includes 1, 2, 3, 4, and so on and so forth. And then we have the whole numbers. These are the natural numbers plus 0. So 0, 1, 2, 3, and so on and so forth. Next is the integers. If you can see here in the number line, we have the negative side and the positive side. So this is called the integers, 0 to infinite and 0 to negative infinite. So this includes negatives. Next is the rational numbers. These are the numbers that can be expressed as fractions, like the negative 1/2 or negative 3/4, or the positive 1/2 or positive 3/4, and so on and so forth. And we have the irrational numbers. These are the numbers that cannot be expressed as a fraction, like the pi, the e, and the square root of 2. Now, together, all these form what we call the real number system. Now that we have looked back on the real numbers, then let me show you the hierarchy of real numbers. So we have here the rational numbers and the irrational numbers. So rational numbers includes the natural numbers, the integers, the whole numbers, and the fractions. And the irrational numbers includes the following: any number that cannot be expressed as fraction, so it's called the irrational numbers. Now, in civil engineering, we have to deal with the numbers daily. So, for instance, a beam, say for example, this is the beam. A beam, a length of 575, say the length is 5.75 meters. And this is a rational number. And also the angle of a slope measured in pi/4, this one, let's take this as pi/4 radians. This is an irrational number. So these are two examples of real numbers: the rational number and an irrational number. Now, let's proceed to the properties of real numbers. Let's look at the properties of real numbers. So these properties make algebra logical and consistent, and understanding them helps prevent calculation mistakes. So the properties of real numbers includes the commutative property, the associative property, and the distributive property. Let's say, for example, in commutative property, a plus b is equals to b plus a, or ab is equals to ba. In associative property, the quantity of a plus b plus c is also equivalent to a plus the quantity of b plus c. So the grouping doesn't affect the result. This is the associative property of real numbers. In commutative, you can change the order of addition or multiplication. In distributive property, a times the quantity of b plus c is equals to ab plus ac. So you multiply each term inside the parenthesis. Just like, for example, we have a beam here. So this is a beam. Let's say, for example, we have two loads. The first load is F1, which is equivalent to 20 kilonewton. And then we have another load at the same beam. We call it F2, and this is equivalent to 15 kilonewton. Now, using the properties of real numbers, we can say that the total load is 20 plus 15. Or we can say that 15 plus 20. So this is the use of commutative property. So using the distributive property, we can distribute the constant across multiple terms in an equation. Let's say, for example, say 3 times the quantity of L plus 2. If we're going to distribute that, it can become 3L plus 6. So what happened here? What happened here is that this 3 is distributed inside the parenthesis. 3 times L is 3L, and 3 times 2 is 6. So this is the distributive property of real numbers. Now, these properties allow engineers to rearrange and simplify structural formulas for easier computation and analysis. Next, we go to the order of operations. And you're also familiar with this. The order of operations. My hands is having dyslexia. Or the PEMDAS. So in PEMDAS, P stands for parentheses. And then E stands for the exponent. Then from left to right, M and D stands for multiplication and division. And then lastly, we have the A and S, which stands for addition and subtraction. Okay, now let's have an example. Let us simplify this equation. How to simplify this? Now, step 1, we have to work inside the parenthesis. That should be the step 1. So, this parenthesis here, so 5 plus 4 is 9. Step 2 is the exponent. So 3 multiplied to itself is 9. So we have worked on the exponent. And then we move on to step 3, which is the multiplication and division from left to right. So see, we now multiply this and then divide with this. So what happened here is we multiply this after taking step 1 and step 2 and this one. So 6 times 9 divided by 9 is 6. Then lastly, we have the step 4. The step 4 is addition and subtraction. So we add 6 to 3 and then we subtract. The final answer is 2. I know that's easy. So for beginners, those who are having hard time in mathematics, this is a good review. So in loads or stress equations, applying the PEMDAS properly ensures accurate results. So a small mistake in operation order can drastically change a computed beam force or bending moment. Next, we proceed to simplifying algebraic expression. Simplify algebraic expressions. And simplifying means rewriting an expression in its simplest equivalent form by combining like terms and applying algebraic properties. For example, if we simplify this expression, 3x plus 2y minus 5x plus 4y, first thing we have to do is to combine like terms. There are two like terms for it with a variable x, so 3 minus 5x plus 2y plus 4y. So we have the combination of like terms is negative 2x plus 6y. So the simplified expression will be negative 2x plus 6y. Okay, so that's how you simplify algebraic expression. So this concept appears when calculating combined loads or net forces. For instance, if one beam carries a load represented by 3x and another by negative 5x, the total load becomes negative 2x, showing a reduction in net force. Next, we'll proceed to the laws of exponents and radicals. Okay. Now, in engineering, we often use powers and roots. For instance, computing area of a circle, which is A is equals to pi times the radius to the power squared, or converting cubic measurements like cubic meter to cubic centimeters. So let's recall the laws of exponents that make these calculations manageable. So these are the laws of exponents. First law of exponent, this is what we call, this is the product rule. The product rule. So this is the multiplying powers. So when you multiply two terms with the same base, for example a, you keep the base and add the exponent. For example, x4 plus x3. So the product will be x raised to 7. So this is the product rule. Next is the quotient rule. The quotient rule, when dividing two terms with the same base, a, for example here, you keep the base and subtract the exponents. Let's use the same example. x4 divided by x3 will be x. 4 minus 3 is 1, sorry. So the quotient will be x. Then the third rule is the power of a power rule. The power of a power rule. So in the power of a power rule, when raising a power to another power, you keep the base and multiply the exponents. So let's say, for example, we use the same example, x to the 4th raised to 3. So we keep the base and then we multiply the exponents. So that's the power of a power rule. And then here comes the power of a product rule. The power of a product rule. Here, when a product AB is raised to power n, the power is distributed to each factor inside the parenthesis. Let's use two variables. Example, xy raised to 4. So the exponent will be distributed to each of the base. Another form is x raised to 4 and y raised to 4. Then lastly, we have the negative exponent rule. In the negative exponent rule, a term raised to a negative exponent is equal to the reciprocal of that term raised to the positive exponent. So let's say, for example, x raised to negative 3, we will move the base from the numerator to the denominator and changes the sign of the exponent, and then we have the numerator 1. So this is the negative exponent rule. Okay, let's make additional examples. If we simplify x squared y raised to 3 divided by x raised to 3y. So how do we simplify this? First, we apply the power rule. How do we apply the power rule? First, we multiply x inside to the exponent outside. 2 times 2. And then we have y 3 times 2. So we use the power of a product rule, the power rule. And then we divide this with x cubed times y. So we have 1 here. This will give us x raised to 4, y raised to 6, divide by x raised to 3 and y. We have still 1. We have an invisible 1 there. Next, we subtract the exponents. Why do we have to subtract the exponents? Because they are in a division form. So x raised to 4 minus 3 c and y raised to 6 minus 1. 6 minus 1. So the final answer will be x y to the 5th. Next, radical roots. In radical roots, we have 2. The first is the square root rule. So what is the square root rule? Now, in a square root rule, the square root of a is equivalent to raising base a to the power of 1/2. Even though there's no number written in the symbol square root, it is understood to be a2, the index of root. The next is the general root rule. The general root rule. So what is a general root rule? A general root rule, so when converting a radical to a fractional exponent, the power m of the base inside the root becomes the numerator of the fraction, and the index n of the root becomes the denominator. So this becomes the numerator, and this index becomes denominator. So the index n was the number on the shelf of the radical sign. It is the root you are taking. For example, the cube root, the fourth root. so it is placed in here. And then the power, m, this is the exponent the base is raised to. So, for example, the radical form will be the cube root of 8. So, this is the radical form. And then, on the other side, we have the exponent form. So, the exponent form for this is 8 raised to 1/3. Another example will be the square root of x raised to 5. The equivalent exponent form will be x raised to 5 over 2. Another example will be the fourth root of y raised to 3 has an exponent form of y raised to 3/4. So these are just a few examples of radical roots and how you transform them from radical form to exponent form. Now, these conversions between radicals and exponents are essential when dealing with nonlinear equations, stress, strain relationships, and growth formulas. So, engineering-wise, you'll encounter exponents like in formulas like moment versus length, which is m is equals to k times L raised to 2, and then k L raised to 2. So this is formula for moment. You also have P equals V GH. So this is the formula for pressure proportional to depth. So understanding how exponents behave ensures you compute dimensions and forces accurately. How do the knowledge of the real numbers help us as civil engineers in understanding the field of civil engineering? So it can be used in measuring beams, concrete mixing, slope showing. But how do these math principles translate into real life engineering? So we can use them as unit conversions. So we can convert square meter to other smaller units. Involves multiplying by powers of 100. In structural formulas, we have simplifying algebraic terms, which helps engineers derive accurate relationships between force, area, and material properties. And also for the load equations, exponent relationships like the weight, and show how the load varies with a square of the beam's length. So every structural design, no matter how complex, begins with a simple algebra and language that lets engineers express and simplify reality into solvable formulas. So that's it for today, engineers and aspiring engineers. You've just reviewed the essential blocks of calculus, the real numbers, and algebraic expressions. In our next episode, maybe we'll tackle about the linear equations and graphs. We'll see how simple lines describe real-world engineering relationships like load versus length and cost versus materials. So don't forget to like this video, subscribe to this channel, and hit the bell so you don't miss the next class. See you next time, and keep learning like an engineer.